inside this disc. Okay, and we have a little plastic cup, and we have a dewar. This is called, it's a vessel, but we actually call it a dewar, D-E-W-A-R. It's kind of a weird name, but it's a vessel for very cold liquids. And inside this dewar is dewar. Inside this dewar is liquid nitrogen. So you have about 70 to 80% of the atmosphere is gaseous nitrogen. You're breathing up. Every breath you take, you're getting tons of nitrogen. And that is liquefied nitrogen. To take a gas and to make it into liquid, you have to compress it and you have to lower the temperature. So this is really cold. Okay, so I'm going to use Kelvin. There's actually 4 different ways of measuring temperature. So you're used to Fahrenheit or Celsius, but in science we often use a more scientific one called Kelvin, K. So room temperature is about 300 Kelvin. So you're at 300 Kelvin right now. This is at 77 Kelvin. This is really, really, really cold. It's actually very hazardous. If I just stuck my finger in liquid nitrogen and I sat it there, I would literally lose my finger. My finger would be, it would freeze my finger, and I could probably slam it against probably break my finger off. Yeah, it'd be bad. Okay, so.
Yeah, who said they wanted to lick that? Yeah. No, maybe not, Sean.
You lose I will feel sorry for your tongue, man. It is going to be bad. Yeah. So I'm gonna pour the liquid nitrogen on the superconductor, and we're going to chill it. We're going to get it cold. So for a superconductor, you have what's called a TC, or critical temperature. So above that critical temperature, the material does not superconduct. There's no Cooper pairs. Below that temperature, and it's different for every superconductor, you get the Cooper pairs that can start linking up and riding the same wave. Okay, so I'm going to chill, and this superconductor is a superconductor, and its TC is above 77 Kelvin. So this is going to get it below that value. This liquid nitrogen will. So I'm going to chill this out and get that puck nice and cold. And then what we'll do is, this is just a metal plate that has permanent magnets on it. Okay? So these little silver blocks on here, and then this annulus that you see are just permanent magnets. And then there's a larger track that has magnets as well. So let's just use this little one. So I'm going to use tongs to get this puck out of there, and let's see what happens here. Okay, so you've seen magnets levitate, but you haven't seen them do some of this other stuff. This is, let me scoot this over. Let's get that colder. Let me let it sit in there a little bit longer. Okay, so if you took, have you talked about magnetism in class? No. So you have probably seen bar magnets. You'll have a north and a south side. So if you have 2 norths, they'll repel. 2 souths, they'll repel. If you put north and south, the magnets stick together. So then you could say, okay, that levitated, but that's just like a north and a north, or a south and a south. No, it's actually not. So let me see if I can get this cold enough, and we'll show you. Okay, so you can see there's that separation, and that may be too heavy. Oh, but if it was just repelling, it would have pushed it down. So it's not only repelling, it's actually latched onto it. It's actually what's called flux pinning. Okay, so that you've never seen a magnet do that. I can assure you that. Okay, this is definitely something a normal magnet cannot do. So it's weird if you if you're actually grabbing a hold, it's actually locked into it. It's really, really bizarre. All right, so that is example of levitation. It actually took a decent amount of force for me to grab that off of there. It really latched onto it.
So their magnetic fields are locked? What's locking?
Okay, so in the superconductor, the superconductor becomes what we call diamagnetic. So what happens is in a normal metal, the magnetic lines, field lines, will permeate through the material. They'll actually go through the actual material. So when that's not below its TC, the magnetic field is like permeating through that disc. This is producing a magnetic field, these permanent magnets, okay? And when you get below the TC, the magnetic field gets repulsed from the superconductor. So it's like rubber bands. It kind of like comes out and it wraps around the superconductor.
Held in
It's held, sandwiched, like rubber bands kind of like strapped around them. And that's what causes that. So, okay, so on this is a similar thing. This is a track that has like kind of a circular track of permanent magnets. All right, let's see what happens if I put the superconductor on there. So, okay, and if I leave it there as it warms up, it'll warm up past its TC and it'll fall. It'll lose its superconductor. So right now the magnetic field from those magnets is expulsed from the material and it's wrapped around that whole. So it's actually hard for me to pull that off. Okay, that's wild. And if I move this around, it has very low friction. It's not like it's. I have glasses on. You don't want that to get in your eye. But yeah, you can see it kind of like drop because it warmed up. Okay, so there's an effort in China and Japan to make transportation systems that are levitation. There's a benefit to this. I don't know if you saw this, but I barely pushed it and it went around several times. If I put this, I put this track inside a vacuum chamber and I sucked all the air out of the vacuum chamber and I put a superconductor in there that was at cold temperature and I made it go around this track, how long do you think it's going to go around that track? Well, it would be a long time. A really, really, really long time.
It's a cold train though.
It is it's just a track. So it would be a very cold, you'd want
It
insulation.
doesn't operate after 68 degrees.
Yes.
To warm it up.
Yes. Yeah, it would definitely be a cold train. Okay, so I mean, that's one kind of exciting application of this. Let's cool this down a little bit more.
Since this will save a lot of power for the transportation,
Right.
I think, but is cooling down everything also consume a lot of power? Is there a better way, or what are the state of the arts on
Well,
cooling
the
down things?
better way is to make the TC at room temperature above, because then you don't have to cool it down.
Yeah.
That's the better way. That's why there's there's tens of thousands of scientists and engineers right now in this world making their entire career on trying to make room temperature superconductors.
But do you think that violates some kind of like law, or do you think that's something we can
No,
make progress
it's
on?
achievable.
Yeah.
Yeah.
Do they keep raising the temperature?
Yes.
Okay.
And I'll talk about that in a second. I can't.
Just when we run out
my
of fossil fuels, we'll have this instead, right?
Okay, so when superconductors were first found, it was 1908, I think. So 1908, there's a gentleman by name of Onnes, And he was a scientist that was just trying to take helium, gaseous helium, like you have helium balloons, and he was trying to compress it into a liquid. And he was successful. He made this refrigeration system, and by the way, he got a Nobel Prize for that work. And he as a scientist, he was like, okay, let me just put some stuff in it at this cold temperature and see what happens. The first metal that he put in there was mercury. Oh, that's cool, because mercury is a metal, but at room temperature it's a liquid. So I would have done that too. I'd say that's cool. So he measured the resistance of mercury at room temperature, and he said, okay, here's the resistance. It was so many ohms of resistance. And then he put it into liquid helium, and it solidified. It became a solid. And he measured the resistance, and he couldn't measure it. His instrument just read 0. For a while, he thought it was a mistake, an instrument problem. It wasn't. That was the very first superconductor. And it just so happened to be, by coincidence, the TC of mercury is the same temperature at which liquid helium is formed at 4.2 Kelvin, which is crazy coincidence. Okay, so they went from 4.2 Kelvin, which is really difficult to do. That's a very difficult thing. I don't have a doer of liquid helium. That's not a thing. Okay, so then they slowly raised this to get above 77 Kelvin, which we can use liquid nitrogen. But now they're at almost Antarctica temperatures. So you can see a clear progression. There's no fundamental physics that we know of that should stop it from getting to room temperature. We just have to solve that material problem. Okay, so that's exciting. That could be happening in your lifetime, in your career. You're talking like with quantum computing, AI, and then like supercomputers. I mean, and then superconductivity. I mean, my gosh, the world could just like exponentially just shoot up.
You guys maybe should have taken some of that comment before it left, because it might help you. Different material.
Could be. Yeah, for sure. Okay, here. One other thing I'll try. Let's put the track upside down. Let's have an inverted track and see what happens. Let's see if we can. Oops. Bet you haven't seen that before.
That'd be a good roller coaster design, right?
That would be a good one. Yeah, for sure. I don't know if I'd be the first person on it.
Maybe not.
Maybe the
27.
thousands person. Yeah, that would be that one. Yeah, cool. So when that warms up, it's just going to fall off. Or it'll fall off. Okay. Okay, and then one last thing. Maybe Sophia, do you want to? This is yeah. So here. So let's go back to the board for a second. You can't have current, and if you have a normal wire, the only way I can get electrons to go around that loop is if I put a battery on that wire. If I take the battery away with a normal wire, the electrons stop moving. This is less like this. This is really a geeky thing, so I'm excited about this, but it's not as visually as cool as a superconductor. But there is a superconductor probe that is at the end of this rod, and this is a little tiny dewar full of liquid nitrogen. So the superconductor that's at the end of this little rod.
Oh, sure.
Yeah,
So this
yeah,
right
yeah.
here, this is called a Mr. Squid. It's a superconducting quantum interference device. So basically, in this probe, this is filled with liquid nitrogen. At the very bottom, there's a superconductor, and we have it connected to an oscillator. An oscilloscope, and basically what this is doing is it's measuring its current versus its voltage. So in normal devices, you're going to see like, you gotta have both. In this, it's really hard to see. I don't know if anyone wants to come up, but it is on right now, and you can see if I move around that it's flatlining right here where there should be resistance. So it's showing current without any voltage. So it's not as cool as this guy, but I mean, zero resistance. So
It is actually displaying zero resistance. I mean, it's showing current, and we've turned off that battery source, and you're getting the electrons moving with no push. The battery is like a push, like you're pushing the electrons around, so we've taken push away, and the electrons just keep moving. That's what that little flat line says. It's not visually all that cool, but people like me get excited about looking at that. That's kind of cool. That would be the test for superconductors. So Fort Lewis College, we're actually ramping up some, we have a algorithm software kind of effort in quantum, but then we have some hardware effort that we're trying to do with quantum as well. So one of the methods of making quantum computing is to have superconducting elements to make qubits, which are the fundamental element for quantum computers. You've heard of bits for normal conventional computers, but then the analogous version of that for quantum computers are qubits or quantum bits. And one way to make qubits is to use superconductors. That's a very heavily researched area. So at little tiny Fort Lewis College, in the lab that made that stuff, which is not superconductors, that's normal electronics, like your cell phone type of electronics, we're trying to make superconducting devices that would be key elements in qubits, hardware qubits, which is shocking for most people to know that Fort Lewis would be dabbling in that, which is pretty fun. So,
Apply to that summer workshop, and you will get a chance to tour the labs, and also even go to the lab and learn how to fabricate all these devices.
yeah, you'd work in the lab that we're doing all this stuff.
The technology is exploding, so we are also purchasing a humanoid robot, which is probably this height, and can do all these kind of stuff like fancy dancing, Michael Jackson style. We're mounting a camera on the top so it can recognize certain objects and follow a person, do some kind of certain tasks. So probably will be the first humanoid robot.
Yeah, it's about this tall. Walk
Yeah.
down the hallway, so we'll that'll kind of freak people out. That'd be cool.
Yeah, so in the summer we will be able to run a lot of demos and some training.
Dr. Lee's gonna bring the robot home in the evenings on the weekends, and he's gonna put it to work on his farm.
Many
Yeah.
applications. I was just in the gym earlier today. I was thinking I was doing a bench, chest lifting. I was thinking I do want someone just standing behind me to
Spot
stop.
you, yeah.
I'm thinking we can get a robot. You can just tell the robot, give a little feedback, saying you can rate from 1 to 10 to tell the robot to give a certain range of strength. Right?
Yeah.
If you are really out of sprint, you can just tell 10, 10, 10, and then lift it for you. Right? So,
Yeah, for sure.
Or heckle you, one more, come on.
All right.
You got Han Solo in there?
So why don't we do this? I'll play around with this a little bit. Oh, one other thing. How much time do we have?
3:30-ish. I think it's before 3.
So
3:32.
let me show you.
15-ish minutes.
Yeah, show you a couple more things, and then maybe just have people come up and just kind of like look at some of these little things. So if you look, like I'm moving this around. This is a 2-inch silicon wafer that has tiny. This is what silicon looks like. The backside. It's kind of gray. Okay, and this is a 2-inch silicon wafer. This is the size of silicon wafers that we process in my lab. So industry, when they make the chips in your cell phone, they use big 12-inch wafers. They're like dinner plates, okay? And they have big, so since they have big wafers, they go into this various types of equipment, and they have all this different stuff done to them. It takes weeks, if not months, to make all these components on these wafers. And then what happens is that they would have a 12-inch wafer, and on that wafer, they would make, like say for instance, 100 different individual circuits. And then they would cut those circuits off of those wafers, and then they would put those little tiny chips. So here's an example. That little square that you see in that opening is a silicon chip. Okay? See the little square right above my finger? That's a silicon chip. And then what they'd do is they would make like 100 of those chips all on one piece of silicon wafer, a bigger version of that 2-inch wafer. So when they make one, they've made a bunch of them. Okay, it's an economy of scale thing. It's called batch processing. And so it makes these cheaper. If they made just one at a time, no one in this room, including all of us, we wouldn't be able to afford a cell phone. They'd be so expensive. Okay, but the fact that they can make so many all in one same process flow. But it takes up to weeks or months to make that little chip. So when they finally get the wafers of all those chips, they're expensive. That wafer is worth a lot of money, okay, in the industry, like the companies that do this. And then they'll dice them up. They'll use a special saw to dice them up, and then they'll put them in a package. This is not in a cell phone. This would be a big cell phone. Okay, the packages in cell phones are really tiny. It's like these little tiny chips, little black chips that you see here. I'll pass this around so you can kind of look at the little chips. Inside those little black packages are little silicon chips. Okay, and they'll package those. Dr. Lee has a lab that can actually do take a little silicon chip and it can connect it to the little package that you see there internally, which is kind of a cool thing to have Fort Lewis has. And that's kind of the big step of how little computer chips are made. So this is examples of tiny little. I mentioned transistors yesterday. So this like for instance, this little, two little like, so just on the end of my finger, you have these two little pads. That is a transistor. That's one single transistor, but the transistor part of it is so small you can't even see it. That's just the electrical connections to access the transistor. The transistor is just so small that we need a powerful microscope to be able to see these little tiny transistors. So you would have like, on a chip this size, we can now, in industry, and just that little chip, not the whole package, we can put over 1 billion transistors in that little area, and it's amazing. They all work, and they're all wired together, and all the wiring works. That's amazing feat.
What does that one look like on the microscope?
Yeah, well you can put it under the microscope when you jump up there and you check it out. Yeah, for sure. Yeah, check it out, for sure. Here, other really quick thing is, one thing I do in my lab is a lot of other projects. This is an example. Guess what do you think this is? Just take a wild guess. It's like just someone rattle off something. What do you think it is? A bug? Kind of looks like a bug in there. Right. This is a miniature human lung. Yes. I knew I'd surprise you on that one. If someone would have guessed that, I would have given you a bonus or something. I'd go get my wallet or something. I don't know. Okay, so this is what's called a lung on a chip. Okay, we made this at Fort Lewis College, and the business end of this is a novel material that had never been done anywhere else on the planet, and we did that at Fort Lewis College. We published papers. I'm sending. Here, this will be motivation to come to Fort Lewis College. So you get, as an undergraduate, you get to do all this kind of scientific engineering work, and you publish papers. I have one student that published 5 papers, journal papers, peer-reviewed papers as an undergraduate. I have 3 students, and I'm going with them. We're going to Honolulu, Hawaii in less than 4 weeks to present a paper. So the students get to fly over to Honolulu and present some of their work in this area. So, I mean, great opportunities at Fort Lewis. The other cool thing, I'll mention this. I'll send this around. Don't take this, don't touch this. This is kind of my past life. There's this little silicon chip in there, and there's a little beveled edge. When I pass it around, you can look at it, just don't touch it. That is a surgical knife made using technology that we do that. That end of that knife blade is atomically sharp. It terminates with one silicon atom. It is the sharpest edge you will ever grab a hold of. I don't know how to make something sharper than an atom. Okay, it literally terminates with a single atom. A very, very sharp blade. The surgeons that we worked with, when they used that, their mouth just dropped when they felt no resistance when they cut into tissue and other stuff. But I'll send this around, take a look at it. It's stuck to a piece of tape on there. But you can see the little beveled edge on there. So all of that stuff is done in labs like this. So you don't just do electronics. We build a rocket engine in that lab as well for rocket propulsion. And Dr. Lee can go on and on about all of his he's got incredible research as well. Yep.
When we were talking about the rocket, I actually was thinking about, because everything now is open source. The we were talking about rockets just launched a couple days ago. And remember the SpaceX, they are able to land a rocket. And I just went online and see a couple people already posted open source, like with the software, hardware, and also the 3D printing models of the rocket which can be landed. It's a DIY landed rocket. This will be one of the projects we're going to do at college, the senior son project.
That's cool. Yeah, that's awesome. But yeah, why don't we stay away from liquid nitrogen? It doesn't hurt you unless it touches you or you touch it. But why don't we get people to start just funneling through? You can come up here and look and we'll interact a little bit. 1, 2, 3.